So good morning and welcome everyone to Taipei into the conference. So let's start the mini course. And our first lecturer is Professor Shigeru Mukai. So he will lecture on Birational Automorphism group of holomorphic Sym-plectic manifolds. Please.
Thank you. Thank you for kind invitation. Where's the chalk? Chalk is here. The last time I visited Taipei is this year, and honorably I gave this lecture after Professor Xu, and then I gave a talk under the title Algebraic Varieties and Symmetry. And my talk is always like that. So essentially same topic, same something. Yeah. But maybe point of emphasis is different. Then this time I talk along the line curve K3 and fan threefold. So this is curve and this is surface. Yes, is it okay? Is something wrong? Freezing. I see. Online is very. May I continue? May I continue? Okay. I always talk over complex number. So this time I was not so well recognized the importance of this guy, Sym-plectic, holomorphic Sym-plectic varieties around this time. But recently I get, especially in the time of pandemic, I learned many things or many developments in this theory. I was involved in 80s, but after that I didn't study so intensively. But now my interest becomes very much, So anyhow, my interest is about symmetry. And roughly speaking, when I gave this lecture, I talked mainly with relation. One of the main topic is relation with automorphism K3 and with relation with Mashu group. And my hope, which I am now trying to get, is the hope. So this extend to Conway group using holomorphic. But this hope is still not achieved. Goal is not achieved. maybe in the last part of my tomorrow lecture, I may mention, but I will try to talk slowly, and moreover, I will try to give a little bit survey of these fields, and I will add my favorite examples for beginners. Okay. So idea is instead of automorphism of K3 surface, I want to consider birational automorphism of higher dimensional Sym-plectic. Or I may abbreviate birational something. Before that, what is known about these higher dimensional Sym-plectic ones, and what are examples? So they are anyhow higher dimensional analog of K3 surfaces, which are characterized by trivial canonical and irregularity vanishes, or H1S. And the world of variety with K-trivial has two sub-worlds, and one is Calabi-Yau manifolds of dimension, for which I don't talk anything in this lecture. And the other sub-world is holomorphic Sym-plectic manifolds, which are characterized by existence of holomorphic two forms, as name suggests, which has nowhere degenerate. But I usually consider only irreducible one. And the name of irreducible comes from Bogomolov's decomposition theorem. Which says up to eta r, or maybe k, I use k equals 0, variety of with trivial canonical class is decomposed into product of complex torus and product of Calabi-Yaus and product of irreducible Sym-plectics. So irreducible means irreducible in view of Bogomolov decomposition theorem. Is this okay? Maybe this is okay. I can't. I want to raise more, but so the problem is really this exists, and that's a problem in old days. But nowadays, many examples is known. And I use notation of S bracket N for small, no, I'm sorry, minimal resolution of symmetric product. And here, the S is surface. You can consider for any dimension, but let me, this, for a curve case, this itself is smooth, but for a surface, this has singularities along diagonals. And it has a nice smooth resolution. And usually this is explained as a Hilbert scheme of n points on S. Yes, this is. And what's good is when trivial S has trivial canonical bundle, then this Hilbert scheme has also trivial canonical bundle. Namely, this resolution is clepant. By using this fact, many examples, not many, but similar examples were found. And so deformation types of non-simple holomorphic synthetic. So first one is K3 bracket N, which is Sn with SK3 and their deformation. And other one exceptional one, which is called OG10. This is 10-dimensional. And let me omit the explanation. Maybe I mention tomorrow lecture, but. And their torus analog. So I omitted the explanation of OG10, but this is closely connected with K3, and first example was construction was made by O'Grady using moduli of vector bundles on K3. And they have a torus analog. One is generalized Kummer, which is take a similar thing for using torus, but so fiber of Albanese map. So this is just a summation map, and with the complex torus. And their deformation. And using a modular vector bundle and its small, its some resolution, one get.
Maybe two-dimensional.
Yes, thank you, thank you. Complex surface, yeah, two-dimensional. So this one is any dimension. Okay. Yeah, this one. But what is surprising in this theory of holomorphic varieties, they are very similar. Not only they are obtained from K3 or two-dimensional complex torus, but they inherit their nice properties of K3s a lot. And what's significant is lattice theory also applies to higher dimensional ones. So in the case of K3 surface, the crucial role was played by H11 part of second cohomology group, which is nothing but the Picard group. And it has, in higher dimensional, it has the same story. But what's surprising is this has also quadratic forms. Or some people say Beauvais Bogomolov or Beauvais Bogomolov Fujiki. Or quadratic form. And one can apply that theory for study of birational geometry of holomorphic Sym-plectic manifolds. And in the study of K3 surface, especially for study of automorphism group, the key role is played by elliptic fibrillation. And this has also natural analog in higher dimensional, which are called Lagrangian fibrillation. En, and people's expect or conjecture, it's called Matsushita conjecture. So this becomes always. But it was not solved yet. Maybe solved in four-dimensional case. Yeah. So I made a quotation mark, yes. Experimentally, all example, we have PN. No other example, but so experimentally PN, yes. But not theoretically. And generic fiber is complex torus. And moreover, Sym-plectic form distributed to this one is zero. So this is Lagrange. The easiest example is consider F. But there's more sophisticated examples also. Yes, so this is a similar part. I emphasize the similarity. But of course, since this is higher dimensional, there's also this distinct phenomena. And what's distinct in higher dimensional? And keyword is the new ingredient is flop. And one can say flop only. So bad news is we have to consider flop, but the good news is that's almost sufficient to handle higher dimension. And this comes from the fact that consider divisor D, which is called movable if complete linear system has no fixed component. Or fixed component, fixed point loci is codimension 2 or more. Or numerically movable if you multiply MD is so, or sufficiently high multiple. And what's good in surface case is when dimension 2 movable implies certain multiple is has no base point. I guess this is due to Zariski, but I haven't read his paper, but to know. And in particular, these NEF. So since S is the surface, C is also divisor, but let me call here curve. And if you insist on curve, this definition works for every dimension. But the bad news is this is normal true in higher dimension. And what the usual process is the usual process is eliminate indeterminacy. Of rational map, or eliminate the fixed point, fixed locus by blow up. But this process break this K triviality. So this is bad news, but good news is when one consider holomorphic sym-plectic manifolds, then flops eliminates fixed log, indeterminacy, or fixed loci, preserving K equals 0. So, and the result is still in the category of the same category. So same deformation types of holomorphic symplectic varieties. So K3 theory on one side, and this is almost honestly generalized holomorphic symplectic modulo flow. And for example, and more, this is this is one thing, and the other thing is thanks to Babitsky and Markman. Already types theorem holds true. One needs some modification, but by these development, one can say, for example, automorphism group of S and automorphism group of holomorphic symplectic one. So this is so for SK3, this is known already by in the paper of Shaffer, Piateshek Shapiro's paper. So yeah. So here, this means there exists homomorphism with finite kernels and co-kernels. I think, yeah, in this case, the natural direction is here. And so automorphism group of K3 surface induces the lattice automorphism group of Picard lattice. But one have to divide this by group generated by -2 reflections. This was classically known, but for in higher dimensional case also you get similar statement where for holomorphic symplectic manifolds, Picard group has a Beauvais quadratic form. Yes. And which are preserved, I'm sorry, by birational. And you can study automorphism group also, but I only consider birational root. And group generated by -2 and other type, which I don't or I can't specify now as a type of reflections. So this is a general background of the whole theory. So I can use this blackboard here. Yeah. Maybe, but is it okay to use the blackboard? I don't know whether it depends on. Maybe I try to keep this one. Okay. So what? Did I set the plan of my lecture? I may keep the 1, 2. So my plan is very modest. I don't prove any theorem, but I want to explain some examples of birational automorphism group. So in this lecture, I mostly the simplest one. So I only mostly consider symmetric product of second symmetric product, and I consider what is birational automorphism group in example. And the example which I consider has the following Picard number. So maybe today I consider this most generic one, and tomorrow I go to higher Picard number case. And so this is X. And the Picard number of this one is sorry, so 2 and 19 and 21. I think as I wrote in my abstract, yes. I discuss including, starting with Picard number 2, I discuss examples including 2 of, so 19 and 20, 21, yes. So let me explain. So this is Is it better? I don't know. Yeah. Okay. Yes. So, example. And first part, I consider S2 and non definition. So S is always K3 surface. And I consider Hilbert scheme of endpoints here. Soon I will specify n equal 2. And this is moduli of ideal sheaves. I don't use this terminology, so don't take seriously. And this is moduli of sheaves with Mukai vector 1, 0, 1. This is just for reference. And this particular case, situation is extremely simple. And Picard group of symmetric Hilbert scheme is canonically isomorphic to direct sum of Picard group of S and some class which I denote by delta. And delta is delta half of exceptional device, where exceptional means S of this resolution. And you have a similar description for second cohomology group. Sorry. And this is embedded. And what is surprising is this is not only isomorphism of a group, but this is also lattice isomorphism. And left-hand side is usual intersection form. And right-hand side is Bobby form. Which is characterized by its nth power is constant times self intersection number. There exists such quadratic form, and self intersection number is proportional to nth power of quadratic form. And this constant is called the Fujiki constant. This only depends on deformation types of holomorphic symplectic forms. And in this, so this exists for all holomorphic symplectic, but in this particular case, yeah, this is very explicit, and delta square. So this is more correctly this Beauvais norm, but let me write in this way, is equal to 1 given by this number. This is related to this number. And in the case of n equals to 2, so n equal 2, then delta square is -2. So this looks very similar to the K3 case, but there are two things which you have to take care. So delta itself is not effective, but only 2 delta has a branch divisor, exceptional divisor, and effective. This is one thing. And another thing we have to think is delta has divisibility too. Namely, the intersection number is always even for all alpha H2 of X. And this kind of thing, this never happens for K3 because H2 of K3 is unimodular lattice. So this newly obtained -2 cohomology class, or sometimes this becomes algebraic, is -2 class as which appears in K3 theory many times, but different from different by them by divisibility. The usual case divisibility is 1, but this delta is -2 divisor with divisibility 2. Okay. So this is a general thing which I have to explain for preliminary for this example. And I consider Picard number 2, so I consider special case, or maybe not special, maybe general case. I consider the case Picard group is Picard number is 1, so the row of S equals 1. So, and hence row of X. Which is maybe basic in basics for study of higher dimensional holomorphic symplectic varieties. And among the basics, there's the most basic example, which I consider so. And I happened to find in 84 is the following. So the special case where, or the minimal degree case, the degree 2 case. Yeah. I think this is a minimal degree case, but I think this is not the simplest. For example, this qualitative case is simpler because you don't need a flop. I studied this case since this has a minimal degree, but I didn't know that fact. This case is not so simple. I was, in a sense, lucky to find this. I consider this example, but by chance. I studied not intensively, but I found this by accident. So, as well known, such case surface is given by, or this is just morphism given by complete linear system of this polarization of degree 2. And since I assume this one, this has no base points, and S is double cover of P2, and branch is double cover, and branch is smooth sextic. Okay, and just to simply consider its Hilbert scheme of 2 points, and consider map to dual plane by associating pair of points, the line joining the image of 2 points. So this is pi. Then this is pi of h. So originally h belongs here, but I abuse notation and same symbol, use same character for Sym-plectic for. Then this has indeterminacy, or this complete linear system has fixed loci. So H is movable, but not free, as I explained in the beginning. This is example of such phenomenon. And where this has indeterminacy, the answer is very simple. So indeterminacy. So map is not defined when pi p and pi q are equal. You cannot determine the line uniquely. There are infinitely many lines. And such a locus, there are nothing but pullback of point of P2. And so this is parameterized by P2. Oh, I'm sorry, P2, I'm sorry, P2 what? Yeah, P2, yes, P2. So this is indeterminate locus has P2. Or base locus is P2. The combination is. And as usual, process tells just make blow up along this P2. Then, fortunately, this pi becomes a morphism. And since P2 is blown up, we have exceptional divisor over P2. And by the simple consideration that simple form restricted to P2 is 0, so this is Lagrangian, that this E is, I'm sorry, okay, this is also an observation is this E is just X and pair. So E has mapped to P2, but also E has mapped to P2 dual. And so this is nothing but the flag variety. And defined by, I'm sorry, defined by the dilation, incidence dilation. This is called flag 3, 4. And as you already observed, E can be brought down in the direction to P2 dual. In the direction of, or not E, but E and blow up of P2 of this one. This one is trivial, but this latter part is non-trivial. And this pi tilde, so this is pi. And pi tilde factors through the blowdown, which I denote by S to U. Yeah, I have still how many papers? Maybe okay. I have to hurry. Okay. So the diagram is this. So we had, so original one is this one, P2 dual. And we have P2 and blow up, and we get E, and this blow up, and we get another blow down, Yes. And this is brought down to P2, this one. And what? And these factors here, yeah, this one, yes. Yes. And this is people call Mukai flop, which I described in that paper in 1984. Yes. So this indeterminacy of phi of h is eliminated by this composition of blowing up and blow down, and now called Mukai flop. Yes. And this kind of thing is generalized, highly generalized by the, they wrote many papers, but let me mention inventions paper of 2015, and they are this kind of things holds in generality. So, but the story doesn't stop here. So what I explained here about the most basic example is this is flop part. But this is also example of Lagrangian fibration. So this rational max becomes a morphism. And what is the fiber of this point of dual plane? Now the answer is immediate. So the fiber, so this pi dual fiber of, I'm sorry, pi star inverse L is Jacobian or Picard variety of degree 2 of pi inverse A. So this is this part is double P1 with branch with branch 6 points, which is intersection of L and branch. And in particular, this is a curve of genus G. So this is abelian surface. And this is an example of Lagrangian fibration. So this example shows two things at the same time. One is this is the example of a flop you have to care about in higher dimension. And the other is this is example of also Lagrangian fibration, which is natural generalization of elliptic fibration, which is key in the study of automorphism groups. Maybe the last observation is maybe appendix, but this is can be also regarded as Touré game or Sarkis-Obrink, or people prefer Touré game. So So we have two Sym-plectic fourfolds, which are birational and transformed to each other by flop. And each has, by this birational, yeah. So this Picard group is not naturally identified by this birational map. And you can consider Nef cone of this side and Nef cone of this side. And they are I don't know what is about. They are joined and become the cone of movable divisors. Move. And this part has so this has extremal ray R1, and this has extreme. Maybe R is better, and this is extremal ray of R star. And this is so I write in peak, and this has is the divisor which contract this R, and this is contract of R star. And this one is given by H, and this one is oh, I'm sorry. Yeah, okay, yeah. And this is given by H minus delta. And this one is, and this is Lagrangian. And the common part of this one is exactly 3H minus 2 delta. And this belongs to perpendicular part of this one. And the situation, so I used all blackboard for one example. So I'm still in this example. And this example can be seen as here flop, and here Lagrangian, and here Turing. And these things are common for here I consider the case where the degree minimum, so this minimal case, but you can consider all degree, but I think other degrees not so explicit, so explicit. I think I can manage H square in this range. And let me explain the largest degree case. So another example. And this degree 22 is very interesting, crucial number for the theory of Fano threefold. So this is the maximal degree. Of prime Fano threefolds. Z minus x. And in this case, degrees. Let me choose a short typical pick V. Yeah. 20. This is. In this case, stories are very similar, but the types of external ray is different. No. I'm a little bit confused. Oh, this one, yeah. Okay. Yes, so in my notation, I call this genus 12. So in this case, so same as this picture, but so this is original contraction. So this gives birational morphism of the resolution of symmetric product. And another external ray R, so this is another ray, is obtained after certain flop. And in this case, we have also, I guess 2, but maybe 3. I forgot to check, but similar model. And the last one has external ray, and this contraction morphism of another ray, different from original one, is contraction. So this is also the divisorial contraction. Yes. So I forgot to say. So in the case of Picard number is 1. So in the case of Picard number of this 2, then in the again is so when degree is square number, then another external ray is Lagrangian vibration. And if not, then and this is divisorial contraction. And I'm now giving non-square case. And also this is the last explicit case at present. And yeah, I'm sorry. So this becomes another model, not S2 itself, but this is S. And this is another model obtained by flop. And this one has contraction, so divisorial contraction. Divisor, so this is divisor, is contracted to surface. Yes, surface, yes. And this is P1 bundle. I'm sorry for that. So example of divisorial contraction. And this X is Debare-Boisson fourfold singular along a surface. And this contraction is morphism is just its minimal resolution. So the fiber is P1, yes. And I guess this is generic, at least I think maybe no has no node along this surface. I forgot to check. And what is the Debare-Boisson? So there are 4 known families which are maximally known maximal algebraic families. Of waffles of these 2 types. And Debare-Boisson is one of them. So one is EPW, which I don't explain, but and the other one is Fano scheme of lines of cubic fourfold, which I explain maybe tomorrow. And the third one is a variety of sums of powers. And the last one is Debare-Boisson. And this is most compactly described, yeah, this one. Debare-Boisson is complete intersection in Grassmannian of this one with respect to vector bundle, this one. So the Grassmannian means this is Grassmannian of 6-dimensional quotient vector spaces of fixed, or maybe this is better to see them. Parameterizing 6-dimensional quotient spaces. And this so this is 6 times 4 is 24-dimensional. And this is tautological vector bundle. So this has all. So tautological means this is rank 6. And this has rank 20. And the complete induction means to take a global section sigma and consider it's the 0 locus. Then you get 24 minus 20 is 4 dimensional. And when sigma is general, you get the smooth ones. But here, sigma is of some special type, and we get this picture. And this is an example. So example. Another interesting example is G equals 6, but I omit. And I go to non-square case. And by that example, I end my today's lecture. Yeah, sorry. Here, this one is H, and I think this another edge is not so simple. H minus 33 delta. And this has degree 22. The same degree, but of divisibility. So degree is the same, but the divisibility is different. So this divisibility is 1. And the prop happens for H minus okay, so let's go to the second case, so section 2. So example of second example, second type of example of S2, and so so this is example of also non-S2 deformation. So this X is at least birational to Hilbert of 2 points, but X deforms to smooth one. This has Picard number 1, and this is example of non-S2 deformation. So, yeah. But the next example is just non-S2 example. There are not so many examples. Maybe this is a unique one. So I only have two papers left, so I think I can manage. So in the case of K3 surface, if you of Picard number 2, and if there's no -2 element, or if there's no isotropic element in PQS, so PQS quadratic form doesn't represent to either -2 or 0, then automorphism group is almost Z, free group, free abelian group. Usually, dihedral group appears. And this corresponds to free unit group of real quadratic field Q square root n, or it's a subgroup of finite index. And this the same holds for SD2 type. And I give example. But before example, I have to explain the following well-known or very important fact. So this is cubic fourfold, which appears very often in the theory of holomorphic Sym-plectic manifolds. And consider a Fano scheme of lines. So lines in V3 inside Grassmannian variety of two-dimensional vector spaces in fixed this P5 is a projectification of C6. I'm sorry, yeah, this is. Then this is a Sym-plectic fourfold. This is the classical result due to Donaghy. I'm sorry, Bobby. They used to show this fact. They used the Paphian cubic, but the following observation is also useful. So when V3 has a node, then you can consider its equation. You write its equation as in this way by taking node 1, 0, 0, 0. Then you can consider intersection of this quadratic and this cubic. This is in P4, and this is K3 of degree 6. This is nothing but the parameter space of lines in V3 passing through this node. And this implies, not directly implied, but in this case, by using some geometric correspondence, this F Fano scheme of lines in V3 is birational symmetric product of this K3 surface. And this implies by general theory, S2 is, so this is birational, this is deformation. Equivalent to so general case, where symmetric for K3 type. So general case, pick X and H square is 6. And in this case, pick S is GH plus Z alpha and 0. I'm sorry. Yeah, this. No, the one. Yeah. And this doesn't give so this is a S2 example. Yeah. So I want to give non-S2 example. This is so they considered the following situation. The situation where there exists a hyperplane section. So this is a cubic threefold, which is determinantal. So this is defined by determinant of dot, 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 dot equal 0. Yes. This, let me name this one. So this is U3. U3 is singular at with rank is 1. This is 6 points. So generically, 6 points. But V itself is smooth. You can construct such situation. And in this generically case, Picard group of F of V3, Fano scheme of lines on V3 is this way. And intersection or Beauvais intersection matrix is this 0 minus 1. So the element, if you write element in this way, then this has 6a square minus 4b square. And movable cone is in this way. So one boundary is h plus 3 over 2 root alpha, and the other is h minus 3 over 2 alpha. And Nef cone is some small part of this positive cone. And how that is characterized, and the answer is as follows. I will soon stop. So the key is this observation. This U has 2 rational map. So this star is this matrix. Then you can solve equation in 2 ways. So star is matrix, and A, B 0. In this way, you get a rational map in this way. And you also solve in this way. And you get A, B, C. And the fiber of this map is a line in U, and this belongs to FV3. And that means you have, we have exist two P2s in FV3. And let's take a line here, and let's take a line here, and LDR, and LDR. Then the boundary of NEF-con is on one side, the perpendicular part of this one, and the other part is L star perpendicular. And movable divisor of cone movable one is just a positive cone. And this is a union of all NEF cone of xn with n runs all integers, and xn's are all so Sym-plectic fourfold birational to original x, and they are transformed by sequence of props. So xn and xn plus. So neighboring two models are transformed by one flop. And in this case, let me use Parachok for the first time. And in this way, you have automorphism group, birational automorphism group. I'm sorry, maybe the header, so let me write in this way. Yeah. So, but unfortunately, this existence of infinite order birational map is only shown by using Torelli's theorem, I guess. No geometric construction, as far as I know, yes. So this is today's lecture, and tomorrow I go to more explicit ones, which I recently studied. So one is Sym-plectic manifolds with automorphism is, I'm sorry, birational auto is finite. And the second one, so this is Picard number 19 case, and this is the next Picard number 21. So this is higher dimensional generalization of Binberg's to most algebraic. This is my plan. Anyhow, thank you for your attention. Yes.
Thank you very much. So do you have any questions? So like for generalized Kummer fourfold, or we can also play the two-ray game, and are there any explicit examples we can?
I very old days, I once tried what? I think I cannot remember soon, but I consider whom two, and maybe P2, yeah, P2, and which comes from 1D, but maybe D is 2 or 4, but 1D polarized abelian surface. And consider this one. Then, yeah, I don't remember where, but I consider something like this, and but no, I think the difficulty is there's not so many examples, but moreover, I think generic fiber is not Jacobian. It's some abelian surface, but the polarization is not principally polarized. So it's difficult for me to go further. Yeah. That's all what I can say now. Yeah, I of course I want to study. I'm also interested in abelian surface. So Kumo is Kumo abelian surface is yeah good target, but no success. I want to ask some participants if you have some idea to, yeah. I am very difficult. It's long open, yeah, project, but which don't, yeah, proceed. Yes.
So are there other questions?
No. This case is okay, but this yeah, yeah, this case is just an example. Yeah, but yeah. Good question. Yeah. You know, no. I think people guess oppositely. One cannot do so. I think I forget to mention, but the big problem in algebraic geometry, open for a long time, is irrationality of general cubic fourfold. This is, and this is, so the general one. General means this V3 doesn't come from K3. So I think this Hassett-Chinkel example is special, but not so special. This is still outside of K3 originated one. So one should try to. so I think this is special, but I think this is still conjectured to be irrational. This V3, yeah. And by the general philosophy around this big problem, this statement implies this Hassett-Chinkel V3 doesn't come from K3. So no? Not K3. Yeah, but then that's probably the component of V3 is It's some tautology. Yeah. The modular point of V3. That's nonsense. Yeah. Yeah.
So are there further questions? Yeah, or are there questions from online? So if there's no further question, then next thanks Professor Mukai again.